Hello, I am Alberto Hernandez Espinosa. I work in AI research with experience in finance and scientific software, and research across biology, physics, mathematics, and artificial intelligence. My background is in complexity science, algorithmic information theory, and causal modeling. Most of my work is directed by the question how complex behavior can arise when time, space, and computation are limited. Most of my work is inspired by the principle of computational equivalence formalized by Stephen Wolfram, that roughly speaking says that you don't need complex rules to get complex behavior, at least in principle. Often complexity comes from the interaction of these simple rules. From that point of view, my research on complexity has two different components. The first is about finding simple causal rules that explain specific behaviors of a system. Rules that comes from the understanding how the system behaves locally and how its components interact. The second part is about what happens when those rules interact. In many systems, the complexity is not in the rules themselves, but in how they combine and constrain one another over the time. Here is where I use algorithmic information theory that provides me a kind of language because it's focused on generative mechanisms rather than the statistical explanations. To ground this, I have selected the paper Language Models Can Perform Single Utterance Self-Corrections of Perturber Reasoning. What I found very interesting about this work is how little it takes to change the behavior of a model. A small perturbation, a single interaction can move the model from one line of reasoning to another without adding any information. This suggests that the model is not following a single internal path, right? This seems to be multiple possible trajectories, and the interaction acts as a way for selecting among them. So the model does not learn something new, but reorganize what is already there. This naturally raises to me some questions like what kind of perturbations work or what kinds of redirections are possible. Obviously, not all reasoning paths can be reachable by one single interaction and those kind of things. I have worked in the same directions. So I have worked with a simpler systems like complex binary networks. What I do is I use perturbations in order to know what is capable to compute this kind of systems. Once I know, I try to formalize this behavior in simple rules, local and of interactions. This is not an easy task because the space of possible behaviors grows very quickly and becomes at certain point very intractable. So this is the result of this experimentation is a kind of compression without losing complexity, without losing information, without losing accuracy. It's possible to replicate this complex behavior by means these kind of rules, resulting in a very high optimization of time and sources. So this does not solve, I know, this does not solve the intelligence in general, and I don't see it as a universal approach, but it does shows that in concrete settings, that explicit causal structure can sometimes replace exhaustive descriptions where the time and space are important factors. From this perspective, I see these agentic systems as relying heavily on interactions and feedback, but without explicitly constructing or manipulating the rules that govern behavior. My interest then is exploring how probabilistic models and explicit causal rules might be combined to improve efficiency and adaptability in constrained settings.